Many thanks to the symposium organizers for inviting me to share some thoughts about music and time. This slide illustrates that musical phenomena exist at multiple time scales that span several orders of magnitude. At frequencies greater than about 10 hertz, we think about individual musical events or musical objects that are characterized by their pitch and timbral characteristics. And then at time scales greater than about 100 milliseconds, we think about the sequences and the timing of sequences of musical events. Between about 100 milliseconds and 2 seconds, perceptual phenomena of rhythm, beat, and meter arise. And then at longer spans, we can think about the organization into phrases or things like verse, chorus, structure in songs, or even movements in symphonies. In this lecture, I'm going to focus on these time scales between about 100 milliseconds and 2 seconds. So if we start with the simplest possible rhythmic sequence, an isochronous sequence in which events are identical and their inter-onset interval is constant. This type of sequence is quite easy for most people to synchronize their movements with. And this synchronization has the characteristic that people are predicting when the next event is going to occur. And this element of prediction in time becomes very important. This is also the simplest illustration of the perception of a beat in the music. Now, if we want to organize at a slightly longer time scale, we can do something as simple as accenting, in this case, the first of every 4 beats. This gives rise to a grouping or a cycle, which then repeats. And this is the simplest way by which meter, or the sense of metric organization, arises. Now, most music consists of temporal patterns where the durations of events vary or the inter-onset intervals vary. And this variation gives rise to rhythmic patterns. And typically the patterns of inter-onset intervals exist in simple integer ratios to each other, so 1 to 2 or 1 to 3 ratios. Rhythmic patterns can facilitate inference of metric structure, and along with that, the sense of the beat with which one can covertly or overtly synchronize. Now, one organizing principle surrounding metric structure is the idea of a metric hierarchy. Shown here is a canonical metric hierarchy where a cycle consists of 4 beats at what's called the quarter note level. But within this cycle, one can have events occurring that are subdivisions by 2 or multiples of 2. And if one simply arranges where all these events might occur at all these different levels, and then tallies up the number of possible coincident events, one arrives at this kind of histogram, which critically serves as a probability distribution that helps guide attention to different moments within that metric cycle. So it's basically a framework for prediction in time in music. So in one of the first neuroimaging studies done to try to understand the brain areas that underlie this sense of beat, Gran and Rowe contrasted responses to various stimuli that do induce a sense of the beat versus acoustically matched stimuli, but where all the onset intervals and durations are random, and therefore there's no sense of metric structure that arises or a sense of the beat. And what they found that when a beat was discernible, sensory motor areas became more active overall, as well as more strongly correlated in their activity. So critically here, the putamen portion of the basal ganglia and the supplementary motor area. Now, this cortico-striato-thalamic circuitry is very important for the specification and selection of actions, a point that I'll return to in a few minutes. Okay, so obviously most music consists of rhythmic complexity that falls somewhere between isochrony and complete randomness, and events are typically constrained to some sort of sense of metric structure. But within that, there's a range of complexity that gives rise to psychological phenomenon referred to as syncopation. And syncopation broadly reflects the degree to which events fall at either more highly predicted or less highly predicted locations of the metric hierarchy. So here's an example of a 3-instrument rhythm, each instrument carrying its own rhythm, but then together creating an aggregate rhythm. And for the most part, these events are falling at reasonably salient locations of the metric hierarchy, though the shaker is also creating events at less salient locations, and this gives rise to a sense of syncopation. Shown here is, below this is an illustration of an output of a feed-forward linear oscillator model of temporal attention that we've used to try to model psychophysics and so on with these types of rhythms. Now, on the right here is an example of a rhythmic pattern that creates a stronger sense of syncopation because events are omitted at expected locations and largely fall at unexpected locations within the metric cycle. So the sense of meter is more difficult to infer, as well as the sense of a beat. And one can kind of see this in the model output there. Syncopation is critically related now to this idea of groove. One definition of this being that aspect of music that induces a pleasant sense of wanting to move along with the music. So this idea that engagement with music is embodied and pleasurable. And Vitek and colleagues, using a broad library of both of rhythms derived both from real pieces of music as well as some synthetic stimuli that varied in syncopation, found that this urge to move and the pleasure is most strongly associated with rhythms of intermediate levels of syncopation. Neuroimaging data from this same group when contrasting medium syncopation, so high groove stimuli versus overly complex and therefore lower groove stimuli, found engagement again of this corticostriatal circuitry by the high groove stimuli, as well as the brain's frontoparietal network that supports working memory and attention functions. So here we have coming together nicely these ideas of deploying attention and time within some sort of metric structure, as well as engagement of the motor systems. Another recent study nicely demonstrated that this notion of meter is inferred. And Lentz and colleagues generated a large library of rhythmic patterns that varied in their level of syncopation. And they strung these together into a sequence, so the rhythmic patterns themselves were not repeating, but the degree of syncopation was either monotonically increasing or monotonically decreasing, depending on which direction they played this sequence in. Now, what they did is they measured the EEG and looked at power in the EEG at frequencies that corresponded to the underlying beat. And what they observed was that within non-musicians, shown here on the left, that when there was a strong sense of metric structures, so weaker syncopation, they found strong coupling at these beat frequencies, but as the amount of syncopation increased and the ability to infer the meter decreased, that coupling with the EEG decreased. Now, importantly, they noticed an asymmetry depending on the direction in which they played the sequence. And this illustrated that this response is not simply a one-to-one direct coupling with the underlying stimulus properties, but rather reflects some sort of mental process of inference. And this mental process of metric inference is much stronger among musically trained participants in whom coupling of the EEG with the stimuli was observed even when the sense of meter or the beat was weaker. Okay, so what we see consistently is this engagement of the brain's action-selecting corticostriatal-thalamic circuitry when people are presented with these rhythmic stimuli, even when they're simply listening to them. In a recent paper by Cannon and Patel, they start diving into possible mechanisms by which these sequences, rhythmic sequences, might generate a prediction of the beat. And referring here to recent evidence that populations of neurons in the supplementary motor area enact short action trajectories. So one can therefore imagine the representation of these rhythms and moments in time that are implied by those rhythms. Interestingly, there's also chronotopic mapping within the supplementary motor area at rates that are within the range of the regular tempi at which music is performed. This is tantalizingly suggests that the SMA might help to coordinate the implementation of particular rhythms, so in which the particular ratios exist between the elements, but that then need to be and can be fairly easily performed at different tempi. All of this exists within a broader organization of the brain, sort of this idea that the brain is designed to support perception action cycles, with the frontal lobe being responsible for organizing actions at a large hierarchy of time scales. And indeed, there's a rostrocaudal gradient that exists throughout the frontal lobe in terms of the corticostriato-thalamic projections that can support, via spiral-like organization of striatal connectivity with dopaminergic areas, the propagation of action plans from very long time scales through to the implementation then of, say, shorter rhythmic musical sequences in music. I'll just acknowledge that there are models of temporal attention. I briefly alluded to an oscillator model. I think I'm out of time though, so I thank you very much for your attention.